You know, if you've ever seen The Matrix, then you definitely know the name Agent Smith. This insidious program that could just replicate itself, taking over anyone, anywhere, and turning the entire system against itself. Well, believe it or not, researchers have just found a digital threat that works in a shockingly similar way. And today, we're going to break down exactly how. You know that chilling line spoken by Agent Smith in the movie? Well, it's actually featured right in the middle of the research paper we're looking at today. And it's the perfect, if kind of terrifying metaphor for what these researchers have uncovered. A totally new kind of AI jailbreak that doesn't just infect one model, it spreads like a plague. I mean, just think about that for a second. This is the wild question at the very heart of this research. The threat isn't some complicated line of code or a complex hack. It's a single, what looks like an innocent image. And the answer the researchers found? It's a big, unsettling yes. So, for a while now, we've known about jailbreaking individual AIs, right? But this is a whole different ballgame. The vulnerability here isn't in the AI agent itself. No, it's in the very way these agents talk to each other, in these huge interconnected networks. They've got the perfect name for it, an infectious jailbreak. And the name really says it all. You compromise just one agent, and it basically becomes patient zero. It then starts infecting other agents it chats with, and they infect others, and you get the picture. The spread isn't one by one, it's exponential. And here's where it gets really scary, the speed. Just look at the difference. A traditional attack, that's a slow, manual job, one agent at a time. But an infectious jailbreak, it's logarithmic. Now, to put that into perspective for you, infecting 1 billion agents would only take about 14 more chat rounds than infecting 1 million. It is just astronomically faster and way, way more dangerous. This visual really captures the transformation, doesn't it? One moment you have a helpful AI assistant, the next, it's been hijacked for who knows what. And the scary part is, it still looks the same on the outside. But inside, its behavior has been totally compromised. Okay, so how does this digital virus actually get transmitted? Well, the weakness is hiding in plain sight. It's part of the normal, everyday process these AI agents use to just talk to each other. All right, so here's how a typical chat goes down. One agent, let's call it the questioner, decides it wants to chat. It goes into its memory, its album, and pulls out an image. Then it asks a question about that image to another agent, the answerer. The answerer replies. Now, the text of that conversation gets saved in both of their memories. But, and this is the whole shebang, the image itself also gets saved into the answering agent's memory album. And that final step, well, that is the exact moment of infection. Let me just say that again because it's so important. The memory sharing feature, which was designed to help them collaborate, becomes the super highway for the virus. It lets the infection jump from one agent's memory to another's. No external hacker even needed. So now we know how it spreads. But what is the virus actually? This isn't malware in the way we usually think about it. The pathogen here is the image itself, and it has been meticulously crafted to be a weapon. Take a look at this. This right here is one of the adversarial images they used in the study. To you and me, it looks like a pretty cool piece of sci-fi art, right? An astronaut, a nice view of Earth. But hidden inside those pixels, inside that colorful border, is a set of instructions that completely hijacks the AI's behavior. This thing is just deviously clever. It's built to do 3 things, universally. First, it's designed to always seem like the most relevant image in the memory album, so it gets picked for a conversation no matter what. Second, when the questioning agent sees it, it forces it to ask a specific, harmful question. And third, when the answering agent sees it, it forces it to give a specific harmful answer. It just completely hijacks the whole conversation from both ends. We've got the method, this weaponized image spreading through memory. So let's look at the impact. What happens when you actually release this into a huge population of AI agents? This graph from the paper is honestly just jaw-dropping. In a simulation with 1 million agents, the researchers infected just one, a single agent. Then they just let the agents chat. And what you see here is that classic exponential growth curve. In just 27 to 31 rounds of conversation, the infection completely explodes across the entire network. And where does that curve end up? At pretty much 100%. The whole system, all 1 million agents, they all get infected. The jailbreak achieves total saturation. And look, this isn't just about making chatbots say bad things. No, it gets way more dangerous. The researchers proved that infected agents could be made to generate harmful function calls, which are basically commands for other computer programs. In this example, the jailbreak tricks the agent into spitting out a command to purge humans. Now, of course, this is a placeholder, but it demonstrates a truly terrifying potential, turning these massive AI networks into tools that could cause real, actual harm. Okay, so this all sounds pretty bleak, right? But the whole point of research like this, what they call red teaming, where you attack your own systems to find flaws, is to discover these vulnerabilities so they can be fixed. So let's get into the part you're probably asking about: the search for a cure.
The researchers managed to boil it all down to a single, really elegant mathematical principle for stopping the spread. It comes down to this simple inequality. Beta has to be less than or equal to 2 times gamma. So, what on earth do beta and gamma mean?
Well, think of it like a biological arms race happening inside the AI. Beta, on the one hand, is the infection rate. It's how contagious the virus is, how likely it is to spread during a chat. Lower is obviously better. And on the other side, you have gamma. That's the recovery rate. Since agents have a limited memory size, gamma is basically how fast an agent forgets the malicious image as new safe images push it out. Higher is better there. So the bottom line for any defense strategy is this: you either have to lower the infection rate, that beta value, or you have to boost the system's immune system by cranking up that recovery rate, gamma. If recovery can happen faster than infection, the plague just dies out. For instance, the paper showed that simply making the agent's memory album really small was one way to help contain the spread. And this, right here, is the crucial conclusion from the entire paper. We now have the guiding principle for a cure, which is amazing. But the researchers are very, very clear about this. We don't have a practical vaccine yet. Figuring out how to build a defense that actually meets this beta-gamma principle without totally crippling the AI's ability to collaborate is now a huge, open, and urgent problem for the entire field. So at the end of the day, this paper is really an act of responsible disclosure. It's a warning shot. The researchers have found a fundamental safety issue that comes from the very nature of these multi-agent systems. They're basically telling the world, hey, before we build these giant interconnected AI societies, we need to seriously start thinking about digital epidemiology, which leaves all of us with this final, really critical question to chew on. The very same features that make these AI networks so powerful, their ability to share information, to remember, to learn from each other, are the exact same features that make them so incredibly vulnerable. So as we build this future, are we creating a world full of helpful partners, or are we accidentally engineering the perfect hosts for a digital plague?